Welcome to Geography 105, Unit 15, focusing on thunderstorms and severe weather. In this particular unit, we're going to take a look at some of the most fascinating storms on our planet, including the storms that produce things like baseball-sized hail, really strong wind gusts, and tornadoes. There's really generally kind of two kinds of folks, really. One sort of group of people that were really fascinated by storms and think that they're remarkable and sort of go outside and watch them. And then another sort of contingent that are really sort of afraid of thunderstorms. So if you're in that second contingent and you're afraid of things like thunderstorms and tornadoes, hopefully this particular unit can help alleviate some of that fear as we will explore and help you understand what's really causing these storms. In addition, the United States, and particularly the Midwest and the Central Great Plains of the United States, are really a frequency hotbed for these particular storms. So every year we see about 1,300 tornadoes across the United States, and Illinois could have upwards of 100 of those every single year. So let's jump right in with thunderstorms and severe weather, Unit 15. We're going to start with a phrase here that I like to mention to all of my intro students and even my upper level students as well, just to remind them that the way we portray tornadoes in our society and in our culture is really sensationalistic. And I want to focus on this second piece here, sensationalism. Tornado sensationalism, the idea of sensationalism just in general is sort of blowing things out of proportion. And we see that a lot with tornadoes in our culture, and I'll give you some examples here. These are just some recent movie covers that I have posted, of course. The Storm Chaser favorite down here, Twister. Everything from, I think we're on Sharknado 5 or 6 now, Atomic Twister, Metal Tornado, right? If I were to ask you to close your eyes and imagine a tornado, all right? So the first question would be, all right, well, where are you? Well, many of you would be in Oklahoma or Kansas or Texas. And what would that tornado look like? How many of you are picturing this long, slender elephant trunk style tornado that's very high contrast? And it's very interesting, right? Look at all of these movie covers. Many of them have that slender, high contrast elephant trunk style tornado. In many of the movie covers, right, there's people running away from the storm as it's causing damage and destruction. So obviously these are made for Hollywood. They're made to entertain. But that really does shape the way we think and we understand and visualize our mental map of, if you will, of what a tornado actually is. So unfortunately, I then bring students out into the field to experience storms via storm chasing and field research, and we come up on a tornado that looks like this. Yes, that is indeed a tornado. Here's the left side of the tornado. Here's the right side of the tornado. This was on May 31st, 2013. This particular tornado is over 2.5 miles wide in diameter. And you can see sort of the top of the tornado here. You can actually even visually see some green in the clouds. You've probably ever heard of the phase, the sky turned green before the tornado hit. That green in the thunderstorm we think is due to the very large hail that was falling. In this case, we had 7.5-inch diameter hail falling from this particular storm. 7-inch diameter, that's the diameter of a compact disc, a CD. So very large hail falling from this storm. This particular tornado was not moving to the left in this image, was not really moving to the right. It was just kind of getting bigger, and if that happens, the tornado is really moving right at you. And this particular image was taken by the Weather Channel and again on May 31st, 2013, and they were doing something called that year called the Great Tornado Hunt. This is what their vehicle looked like. They were out basically providing weather information or videos and pictures in a live feed back to the Weather Channel. And this particular tornado hit them. They were not prepared. This tornado was moving very fast, over 70 miles per hour. And the Weather Channel, right, the people who are supposed to be bringing you the coverage of these tornadoes actually got hit by this particular tornado. This tornado was actually thrown, this vehicle was thrown 300 yards, and everybody inside thankfully was turned out to be okay. Some minor injuries, probably because of the larger vehicle that we're driving, but there were 3 storm chasers that were actually killed in this particular tornado. So it sort of reminds us that these tornadoes can be very damaging both on the surface, the physical landscape, But many times, if you have family members or friends that have experienced very bad storms, they often leave mental scars as well. So much of your life is then binned into a category. What happened before the tornado? What happened after the tornado? Is these things can obviously destroy your home, destroy your livelihood, even take family members from you. So they can be very devastating events. And then obviously from a scientific perspective, very fascinating in terms of their wind speed, their pressure, just very anomalous in terms of what we experience with these particular storms. Here's an example of the impact on the physical landscape. This was in early May of 2011. You're looking right down on Joplin, Missouri High School and the surrounding neighborhoods. You can see all the homes there. You can see the roads. You can see the looks like tennis courts and a softball diamond and a baseball diamond track and so on. This was some aerial photography taken before the tornado. And here's a picture as it swipes to the left after that tornado hit. So you can just see unbelievable destruction. Almost every single home in this neighborhood was damaged. The high school sustained a roof collapse and major damage. The tornado through here was rated EF5. So in this case, let me put the F in there for you. The scale that we use to rank the tornadoes, which I'll talk about in just a little bit, is the Fujita scale. And in the early 2000s, it was updated to be called the enhanced Fujita scale because we got some more wind damage indicators to help us better understand these ratings. The scale goes for 0 through 5, and so the most powerful tornado being rated EF5 and the weakest tornado being rated EF0. And we'll talk again a little bit more about that in just a second, about that rating scale. Okay, let's start off with some basics though. This is thunderstorms and severe weather, so the tornadoes have to come from somewhere. They come from thunderstorms, and so we'll start with the very basic definition of how would you define a thunderstorm. Turns out that can be very difficult, but the most simple definition of how you would define a thunderstorm is a localized storm produced by a cumulonimbus cloud. So from our clouds lecture, right, this is a towering, vertically developed cloud. It's always accompanied by lightning, and if it has lightning, then there is thunder. Sometimes in the summer, you might see lightning and not hear any thunder. The storm can be very far away. That's sometimes called heat lightning, but there is really no such thing as heat lightning. It's just lightning that's too far away to hear the thunder. So, now with the definition of a thunderstorm, really what I want to focus in on the first part of this lecture is the ingredients for storms. So in other words, you want to bake an apple pie, you need flour, you need sugar, you need water, you need apples, etc., etc. We'll talk about the ingredients necessary to create these thunderstorms. We'll talk about the life cycle of storms. We'll talk about the different types of thunderstorms, all ranging from the single cell thunderstorm that usually doesn't produce severe weather, all the way up to the queen, really, of storms called the supercell that can produce grapefruit-sized hail, larger, and significant tornadoes. First question, where are thunderstorms most common? You might right off the cuff say Kansas, Florida, right? Texas, Seattle, I don't know, I get Washington State. I get all kinds of answers for this. The answers for where thunderstorms are most common in the United States is really Florida. Without a doubt, Florida sees the most number of thunderstorm days every year. You can see over 100 days in right near Orlando, where we put one of the world's largest outdoor parks in Disney, right? The reason for this is due to the unique geography of Florida. So Florida is a peninsula, and what generally happens throughout the day, we know now from meteorology, land heats up faster than water due to the differences in specific heat. So as the land heats up, a little local area of low pressure is created over the Florida peninsula. The wind then basically goes from high to low pressure, converges inland. We get something called the Florida sea breeze that's established. That sea breeze helps convergence and initiation of thunderstorms almost on a daily basis in the summertime over Florida. So you can see really there, you look at least across the lower 48 and big bullseye there in Florida in terms of number of thunderstorm days. You can see as you go from, like, say, New Orleans towards Chicago, the number of thunderstorm days decreases anywhere from 80 to 90 thunderstorm days per year in Chicago, we generally see somewhere between 40 and 50, maybe 60 thunderstorms days per year in a really active year. And you can see that, so that sort of tells you right away that, proximity to the Gulf of Mexico really does make a difference here. Although southern Texas, we'll see, doesn't get very many thunderstorms compared to, say, New Orleans. So there's something else going on there as well. There's really an elevation component here that I haven't mentioned. If you go from Chicago to Denver, you can see the number of thunderstorm days remains relatively constant until you get right out on the Front Range, where the number of thunderstorm days jumps by about 20 to 30 every year. And so we can see that mountains play a role as well. Places like Seattle and Portland and San Francisco and so on, LA, are very rare to get thunderstorms out there. In fact, under 10 per year thunderstorm days. So again, these are not tornadoes. This is just a storm that produces lightning and therefore produces thunder. You might associate Seattle with a very rainy place, and it is a very rainy place in terms of precipitation. But not a lot of that precipitation actually comes from thunderstorms. You can see only less than 10 days. So this is, again, the just very broad overview of the average number of thunderstorm days in the continental United States. And this was basically taken over a 30-year average. Another way to look at this is just count the number of times that lightning flashes. We have a global observing network that observes lightning flashes, and so then we can just bin them and count them and see, well, how many lightning flashes do we see per year. And you can see here, this is basically just a density map, so the number of flashes per square kilometer per year. And again, Florida shows up really nicely in terms of a hotspot for lightning activity. And really, most of the eastern 2/3 of the United States see a lot of lightning activity, Maine sort of being excluded from that. And the lack of thunderstorm activity across places like California, Oregon, and Washington is also noted. So, if you want to create a thunderstorm, if you're the atmosphere and you want to create a thunderstorm, what ingredients do you need? All thunderstorms need 3 basic ingredients. They need moisture, which is really the fuel source. So if you were filling your tank with gas and you wanted to drive your car, you'd have to put gas in there, right, to fuel it. For thunderstorms, you need moisture. So we'd like a hot, really muggy atmosphere in order to create thunderstorms. You also need instability, which is a measure of how unstable the atmosphere is. And generally, when we talk about instability, we're looking for really cold air in the upper levels and really warm air in the lower levels. And warm air, right, is less dense, so it has a tendency to rise. And what we'll really want to happen here is that the cold air and the warm air will want to trade places. And when you have an atmospheric situation that is set up like that, warm, humid air at the surface and cool and dry air aloft, it's like oil and vinegar essentially. These densities are different, and the airs want to basically exchange locations, exchange places. And when that happens, that's a very unstable atmosphere, right? That would be different than having the cold air below and the warm air aloft. The warm air would want to stay aloft and the cold air would want to stay down low. That would be a very stable atmosphere. So in this particular case, warm air at the surface, cold air aloft, that's unstable. That can help create this lift, this upward vertical motion that's necessary for severe storms. In order to get that process started, so what's necessary to get that updraft rising up through the atmosphere? You need a lifting mechanism. Now, lift comes in many different ways. You can have mountains, right? So if you have a big mountain range and air is flowing towards that mountain range, it can't go into the mountain, it's got to go up. And so mountains can provide lift. Fronts can provide lift. So if you have a cold front on a map, right, and this is relatively cold air, say CP air back here, maritime tropical out in front, that maritime tropical air, right, this is cold dense air hugging near the surface. If something as that cold front progresses, it can lift that maritime tropical air up into the atmosphere and create thunderstorms. So really right here, and I guess there's an acronym that we can use here. So lift, instability, moisture, right? LIM. Those are the 3 basic ingredients for thunderstorms. When you add the S to make it slim, The S is required for severe thunderstorms. So when I say severe thunderstorms, we're talking about 1 inch or greater hail, so 1 inch diameter or greater hail, wind gusts greater than 50 knots or 58 miles per hour, those are the same, and or a tornado. So in order to get the thunderstorms like this, right, these big severe storms that produce hail and tornadoes and damaging wind, we need the shear component. The shear component comes in 2 flavors, and I'll talk about that for just a second. So if you want to remember the ingredients for thunderstorms, the very simple acronym is SLIM: shear, lift, instability, and moisture. Let's talk about each of these ingredients individually. Where does moisture come from? If you're talking about severe storms or thunderstorms in general across the U.S., the moisture is coming from the Gulf of Mexico in many ways. So if you can imagine yourself here on campus, if you want to have thunderstorms, you're probably going to have a surface wind that's coming from the south. Why? That's where your maritime tropical air mass is. That's where your moisture is coming from. The source of moisture for severe storms and thunderstorms in the United States is, without a doubt, the Gulf of Mexico. If you're talking about thunderstorms in the desert southwest, like the monsoon season, most of that moisture is maritime tropical, but it's coming from portions in the tropical Pacific. So you get a southwest wind there, it brings that moisture inland, and you can get daily thunderstorm activity in July and August in the desert southwest. It's called the North America monsoon. But generally, if you're talking about tornadoes in the Great Plains of the United States and the Midwest, most of that moisture is coming from the Gulf of Mexico. Instability, as I tried to draw before, is really just a measure of how unstable the atmosphere is. The atmosphere is unstable when we have warm, moist air at the surface and cold, dry air aloft. That warm, moist air is less dense, it wants to rise. The cold, dry air is more dense, it wants to sink and be near the surface. So when we create this situation in the atmosphere, we say the atmosphere is unstable, and that if this air is given a little upward nudge, it will continue to accelerate like a hot air balloon upward in the atmosphere. Here's some examples of lift. I mentioned before, we can get lift from topography, we can get lift from fronts, we can get lift from actual weakening other thunderstorms. So as a thunderstorm goes up in the atmosphere and then it comes back down, right, that air coming down can hit the ground and spread out in all directions like an outflow ring. We call those outflow boundaries, and those outflow boundaries, right, wherever they are, this would be a cold pool of air near the surface, can actually generate new thunderstorm activity on the leading edge of those outflow boundaries, those outflow rings. So lots of different ways to get lift in our atmosphere, but you need that initial upward motion to get that unstable air moving up to create thunderstorms. Here are some examples of shear. Okay, so we talked about shear being necessary for severe storms in particular. In profile A, this is a wind profile, so imagine a flagpole with respect to height. Situation A is what we call speed shear. So speed shear is essentially just the wind increasing speed with height, right? So from the lowest levels of the atmosphere to the mid levels to the upper levels, the wind is not changing direction, it's simply changing speed. So in this example, we have a wind out of the southwest. It's increasing from 10 to 20 to 30 knots. Shear can also come in the variety B, which is directional. In this case, we have a wind coming from the southeast at 20 knots, changing to the southwest at 20 knots in the mid-levels, changing to perhaps west-northwest at 20 knots in the upper levels. In this case, there is no change in speed, right? 20, 20, 20, but there is a change in direction. And you can imagine if there's a change in direction, that basically creates this kind of corkscrew nature to the wind profile, and that does indeed lead to storm rotation. And so one of the real precursors for supercells, as we'll see here in a second, in tornadoes is to have some turning of the wind with respect to height, some directional shear. If you combined A and B, you may get a profile that looks like C. C is what we call speed and directional shear, where the direction is changing with height, but we are also changing speed. We go from 10 to 20 to 30, and we also go from southeast to southwest to west aloft. And in this particular case, if you really want severe storms and supercells, you'll be, as a forecaster, you'll be looking for wind shear profile C, where we're changing speed and direction with height. It's a storm, so it has a beginning and an end, right? So let's talk about the stages of thunderstorm development. And these are somewhat different depending on the type of storm that you're discussing, but all storms generally go through these 3 stages. The first stage of a thunderstorm is what we call the developing or cumulus stage. In this case, in this particular stage, the storm is dominated by updraft. So we have no downward rushing air to the surface. All of the air is going upward. In this particular case, probably mid to late afternoon, you look outside, you see some puffy cumulus clouds that are starting to vertically develop. Okay? This vertically developed process is called the cumulus stage. It's dominated by updraft. And what you'll see here is right around this area where we cross the freezing line, we'll start to have, right, of course, liquid water down here in this portion. Let me get rid of some of this. We'll have liquid water down here below the freezing line. Above the freezing line, we may have some ice crystals and some super cooled liquid water droplets where the Bergeron process is just beginning to occur. So probably not lightning just yet, but as the storm continues to mature and the Bergeron process starts to really dominate above the freezing profile, then you may start to see some lightning strikes out of the cumulus stage. But generally during the cumulus stage, we see no precipitation, we see no lightning, just some vertical development of these afternoon cumulus clouds. As the updraft continues to strengthen, the storm may enter the mature stage, where we have now a well-established and vertically developed cumulonimbus cloud that may be reaching upwards of 40, 50, even 60,000 feet, depending on the time of the year. You'll notice here the updraft can be quite strong, hundreds of miles per hour in some cases when you're talking about supercells. But the other thing here is that we also have a well-established downdraft, right? So we have a portion of the storm that is upward vertical motion and a portion of the storm that is downward vertical motion. Of course, if you're underneath the downdraft, you're experiencing heavy rain, perhaps gusty winds. The air is much colder as it's really descending from a much higher location in the atmosphere. Notice also how the freezing profile is changed depending on if you're in the updraft or the downdraft. Of course, if you're in the updraft of the storm, the freezing profile is slightly higher. If you're in the downdraft of the storm, the freezing profile in the storm in terms of height above ground is slightly lower. So this is really the process. This is, by the way, too, when thunderstorms are at their peak intensity. So if you're looking for severe storms, things like hail, damaging wind gusts, it's probably going to happen during this mature phase of the storm. And again, storms all have an end, so they do go through a dissipating stage where they're predominantly downdraft. In this particular case, you might just be experiencing some sprinkles at the surface or some very light rain. You notice there's really no updraft from the surface anymore. There might just be a little bit of upward vertical motion above the cloud base, but most of the storm now is dominated by downdraft, and really the storm is over at this point. And just by the way, from a philosophical perspective, if you look at these 3 stages, you might ask, what's the point of a thunderstorm in general? The point of a thunderstorm is to really alleviate the instability that's present. So it's done by taking this warm, moist air, bringing it up into the atmosphere, and really mixing the vertical profile of the atmosphere through a process, this energy transfer process of convection. Right, so convection is the vertical transport of energy in a fluid, and that's really why we call it severe convection. It's an energy transport mechanism. So these thunderstorms occur on a daily basis across the globe to really alleviate the instability that has built up throughout the day or throughout the week. There are different types of thunderstorms depending on wind shear profile. So this is really a function of wind shear. If you have 3 basic ingredients, lift, instability, moisture, you will get a thunderstorm. The type of thunderstorm is dependent upon the wind shear. So if you don't have a lot of wind shear, you will probably get something like a single cell, or what we call air mass thunderstorm. Air mass thunderstorms essentially have an updraft that goes straight up, and the downdraft that comes straight down. You can see them in these pictures here. This is taken off the coast of Florida. We have some inflow into the storm. The air goes straight up and it comes straight down. All right, we have no wind shear, so there's not a case where the wind, right, is pushing or the updraft is tilted in nature as it rises. The air in this particular case is probably doing something like this, right, where we have air moving from left to right and it's barely changing speed. And so as the balloon goes up, right, the balloon basically comes back down in this particular case because there's no wind shear. These storms are relatively short-lived, about 30 minutes. They're relatively weak. They don't generally produce severe weather, but they can produce heavy rain and lightning. The next step up in terms of severity would be sort of an army of single cells, which we call multicells. These are groups of thunderstorm updrafts that occur when the wind shear profile is a little bit more organized, so you have some speed shear or perhaps some directional shear. These cells can conglomerate into basically self-organizing systems called mesoscale convective systems, or MCSs for short. These mesoscale convective systems, as you can see here in both the schematic drawing on the top right and the actual observed picture on the bottom right, can be a little bit more intense than your single cell storms. These can produce especially damaging wind, but they can produce small hail and also occasionally some weak tornadoes. These sometimes occur along the leading edge of cold fronts. If that happens, we call them squall lines, as you can get a long line of thunderstorms that produces heavy rain, widespread wind damage, and also a lot of lightning. So this generally requires a little bit more wind shear. You can kind of see here in this picture. This happens quite a bit when you get some speed shear. So in this case, we have wind increasing with speed, with height. It basically just separates the updraft and the downdraft of the storms to allow the storm to live a longer life cycle. Keep in mind, these single cell air mass storms, if I go back here, one of the reasons that they're so short-lived is the updraft basically goes up and then the downdraft chokes off the updraft. It comes right back down on top of the updraft, really not allowing this storm to live a long life cycle. On the other hand, when you have this speed shear, so the wind increasing speed with height, you can separate the updraft and the downdraft, and that allows for a further longevity of the storm's life cycle and really a more severe, generally we call this organized convection. It's a little bit, it's not random, it's not just popcorn thunderstorms. These are storms that last for a little bit longer in terms of their life cycle. They can actually last for days in some cases, and they generally produce a little bit more severe weather due to their organization. A type of mesoscale convective system is the squall line. So the squall line is generally found along, in this particular drawing, a cold front. I'm sure you've seen squall lines before. If you live in northern Illinois or live in the Midwest, you probably see these big shelf clouds coming along the horizon. If you stand and watch those shelf clouds, you'll feel the wind at your back sort of feeding the updraft of the storm. And then many times as these storms get closer, the wind changes direction 180 degrees and you'll start to feel the cool outflow and then eventually the precipitation from these particular storms. These squall lines can produce gusty winds and heavy rain and lightning. They're generally not tornado and hail producers, although it's not out of the question for that to happen. But they generally in the Midwest produce very beneficial rainfall for agriculture. Here's an example of what a squall line looks like on the WSR 88D radar profile. So you can see this ribbon of higher reflectivity. You can see the values over here in the right. So as we go to the oranges and the reds, essentially what that means on a radar view is that the precipitation is getting more intense. So the heaviest clusters of storms on this particular radar imagery would be circled here in blue. That would just be where the rain is heaviest. And then of course we can animate these pictures to kind of show what that looks like with respect to time. So let me animate that one more time for you. You can see the progression of this particular squall line. And so, some of the heaviest rain is occurring down here, and in this portion of Boxnet County there, that's probably where the storm is most intense. That area might have a severe thunderstorm warning telling people to get indoors because of high wind speeds and perhaps some small hail. I wanted to provide one slide on these mesoscale convective systems because there are a few questions about MCSs in the AMS Weather Studies lab packet, so I want to make sure that you understand what these are. These are really, the definition of these here are self-sustaining large thunderstorm clusters that meet a certain size or time criteria. In fact, if you look at the word mesoscale convective system, it's just a fancy way to say a thunderstorm system that's about the size of the state of Iowa. So that's what mesoscale means. So mesoscale is a type of scale of meteorology that focuses on relatively small time and space scales. That space scale is about the size of the state of Iowa, which I have circled here in the lower right. So these thunderstorm clusters are, again, about the size of the state of Iowa in terms of their spatial extent. They're large, self-sustaining thunderstorm systems, and they produce a lot of very beneficial rainfall in the Corn Belt of the United States, which really extends from southern and central Indiana into northern Illinois, out into Nebraskas and Dakotas. So this general area that I have circled there in red is known as the Corn Belt of the United States and produces a lot of the world's corn and soybeans. And these thunderstorm complexes produce a lot of that very beneficial rainfall in the summertime. If you've ever been woken up at 2 or 3 o'clock in the morning in July or August, it's probably from one of these mesoscale convective systems that's running across the Midwestern states, producing heavy rain, lightning, and some very beneficial rainfall in many cases. Of course, if you get too many of these in a row, you'll have to start dealing with things like flooding, but generally they are very beneficial rainfall producers. And then we have really the king or queen of all storms, thunderstorms, which is the supercell storm. Supercell is named for its rotating updraft called a mesocyclone. So a mesocyclone is a fancy word for a rotating updraft. All supercells have mesocyclones, and in this particular case, you can actually see the images drawn here. These storms, if you animate them in time lapse, will have a corkscrew, a rotating updraft. And of course, that rotation inside the storm, you can imagine, would be a precursor to things like tornadoes. But these mesocyclones can produce very large hail and surface winds that are very damaging in excess of 100 miles per hour. So a majority of the really bad severe weather that we see in the United States comes from these enormous rotating thunderstorms called supercells. They are organized. They can actually last for many, many hours producing tornadoes and severe hail. So these are the ones you really want to watch out for in terms of damage to life and property. Here's a picture of a supercell thunderstorm in the western Great Plains of Kansas. And one thing that you can see immediately already is that there is a large degree of wind shear in this picture, where you can actually tell the updraft of the storm. Here's the little funnel cloud or perhaps tornado if it's touching down. The inflow in this particular air is rising and then also being, in this case, pushed from left to right in this image as there's lots of vertical wind shear present. You can actually also see the striations in this particular storm if I'm drawing on here. So good indication that this storm is rotating. In this particular case, the air is actually going something like this in terms of a rotation. So many of these storms rotate counterclockwise due to the Coriolis force in the northern hemisphere. You can see the anvil of the storm way up in here, the updraft of the storm, and then lots of these little anvil crawlers that are coming out of the updraft. Supercells in many cases are just beautiful display of Mother Nature's power. Here's another picture of a supercell from a different angle. This one is backlit by the sun. You can see the updraft. Here's the tornado down here at the bottom. You can see the updraft of the storm really comes right through the tornado and produces these really cauliflower cumuliform updrafts. The more, in general, if you're outside watching thunderstorms, the more crisp, the more cauliflower look that the cloud has to it, the stronger the updraft is, and probably the more severe that storm is. If you see updrafts that kind of look like mashed potatoes or really mushy, that's probably an area of the storm where the air is not rising or ascending through the atmosphere very fast. So one visual proxy that I like to use when I'm out in the field is the more crisp the updraft, the more cauliflower in nature of the updraft, probably the stronger the updraft and the stronger that storm is and the more potential it has to produce severe weather. Another look at a supercell. This one you can just visually see without even going in time lapse is rotating. The tornado here on the left, in this particular case, very strong rotation in this particular storm. And again, these storms really come to life when you look at time lapse photography. So I invite you to go on Blackboard to the weather links and take a look at some of the links that I posted there for different time lapses, the sky lapses that you can take a look at. It's amazing to see what these can do when you look at them visually through time, and you can definitely see that these things are rotating and obviously then have the tendency to produce things like tornadoes. On radar imagery here, what you'll probably see is an echo on radar that looks somewhat what we basically call a hook echo. So the supercell on radar has right at the tip of the southwest corner will have something called a hook. This is the area of the mesocyclone where we have rotation in the storm. The tornado in this particular radar image would be located right at the center of the hook. Visually speaking, we generally have a big rain-free base, an updraft of the storm. You can see the updraft actually coming into the storm. We can see the rear flank downdraft coming in from the other side. But on radar imagery, you'll probably be looking for a feature that looks something like this. That's a great indication that the storm is a supercell and has the potential to produce some of those hazards that we just mentioned. If you're more interested in learning, more about supercells, I invite you to take Geography 306, which is severe and hazardous weather, where you focus a little bit more on the structure of these storms and the hazards that they produce. But there are a lot of great resources out there online in terms of identification and visualization of supercells. And if you're interested, you can also take a severe weather spotter training seminar that are free and offered every spring through the National Weather Service that cover storm identification, visualization, and tracking in a little bit more detail. And again, those are offered every spring through the National Weather Service. You just kind of have to keep your eye out on a website to get trained and become a trained spotter. So I've talked a lot about severe thunderstorms, and I very quickly mentioned the definition. But in the United States, we have a specific definition of what a severe thunderstorm actually is. You might think, well, is it the number of lightning flashes? Is it how strong the wind is? Is it how much rain falls? The criteria that we use in the United States is really these three. So we have to have a thunderstorm having 1-inch diameter hail, surface wind to 58 miles per hour, and or a tornado. Now, you don't need all three of these, you really just need one. So if the storm produces a tornado but no hail and no wind, it's severe. If it produces wind with no tornado and no hail, it's still severe. So all you need is one of these criteria to meet severe weather criteria. Severe storms tend to occur near fronts. They're most common in the spring and early summer across the US, although they can happen in any month in any state. And generally, severe thunderstorms have vertical wind shear with tilted updrafts that help them sustain cell life, as we previously mentioned. So if you're looking at the spectrum of severe weather threat, it's sort of minimal threat down here with these single cell air mass thunderstorms or these popcorn showers. These are most common in maritime tropical air masses in the summer. Think Atlanta, think Orlando, think New Orleans in the summer. These storms go up, they last for 30 minutes, they come down, and you're done. As you introduce wind shear and the storms become more organized, the threat for severe weather increases all the way to the top of the scale, which is your rotating supercell thunderstorm, which has a very high threat for severe weather due to its persistent rotating mesocyclone updraft into the storm. Another hazard that's not considered to be focused for severe weather but does kill about 100 people per year in the United States is lightning. Lightning is really just a discharge of electricity, so built up charge separation in clouds. There's lightning that strikes from cloud to another cloud. There's lightning that strikes from cloud to ground. So some lightning strikes do actually come down and hit the surface of the earth. You'll see that most of them are within the cloud or from cloud to cloud, about 80%. But 2 out of every 10 lightning bolts actually come down and hit the ground. Those are the ones that you have to be worried about if you're at the surface of the earth for getting hit. Temperatures in lightning strikes can reach hotter than the surface of the sun, 30,000 Celsius. That very rapid heating causes a very rapid pressure increase, causing a shock wave away from the lightning bolt, which is the thunder that you hear. You can only hear lightning on a good, calm, clear night if you're about 12 miles away. If you're further than 12 miles away, depending on the time of the year and depending on the atmospheric profile, you probably won't be able to actually hear the thunder. And that's what you have heard of probably before in regards to heat lightning. There really is no such thing as heat lightning. It's just lightning with thunder that's too far away to actually hear the thunder. Lightning goes through a process. You can see here A, B, C, D. It starts with this stepped leader process, which is shown in B. So it's this little quick discharge away from the cloud. You'll see it happens because of the charge separation. We're at the top of the anvil. We get a lot of positively charged particles in the cloud. Near the base of the cloud, we have a lot of negative. Then the stepped leader process starts discharging towards the ground, where we have a lot of built up positive charge. We then sometimes see a streamer, which is the little, you can actually see in this photograph over here, but it's a little discharge coming from the bottom up that sometimes meets the stepped leader as it comes down to C. You don't always see the streamer, but sometimes it is there. By the way, the stepped leader process, B and C, these are both processes that you cannot see with your naked eye. They happen way too fast. The only thing you see with your naked eye is part D, which is the discharge or the return stroke, where we discharge all these positive ions back up to the cloud and get alleviate the charge separation that happens. So sometimes if you see lightning flickering, it's just a lot of different, it's basically pulsing in the return stroke of the lightning that is then visible by the naked eye. But the step leader process and the streamer process happen way too fast for you to visually see with your eye. You need high-speed cameras in order to capture that. And let's see here, I could probably pull up a video of some very high-speed lightning strikes. Let's see if I can do that for you here. Let me bring this over so you can get an idea of what this looks like. See what these slow motion lightning strikes look like. So in this case, we have a high-speed camera that slows down in many cases like 60 to 70,000 frames a second. You can actually see the If you've ever been outside and seen lightning and started counting before to try to figure out how far away the storm is, that is legitimate, right? Light travels much faster than sound, right? Light travels at the speed of light. Sound travels about 1,000 foot per second near Earth's surface, given the pressures and densities, assuming some constant temperature. That's about 1 mile every 5 seconds. So what you can do when you see the lightning strike, start counting. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5. Boom, you hear the thunder. Take that time, which was 5 seconds, divide it by 5, and that's the distance in miles that the storm is away. So if it takes 15 seconds for the thunder to occur after the lightning, 15 divided by 5 is 3, the storm was about 3, that lightning strike was about 3 miles away. So it's a very easy back of the envelope calculation to try to figure out how far away that lightning strike was. Of course, if you see lightning and you start counting 1 in 1,000, you don't even make it to 1. That's 1 divided by 5, right? That's it. That lightning strike was less than a quarter mile away, and it's definitely way too close for you to be standing outside. But we use this very simple rule of thumb to try to calculate the distance away from the lightning strike. So the other thing too is if you start counting and you go 1, 1,000, 2, 1,000, you get all the way to 60. 60 divided by 5 is 12. You're probably not going to be able to hear the thunder. So once you get to 60, you might as well just stop counting, because it's very likely that that lightning strike was too far away for you to hear the thunder. Every second across planet Earth, there's 50 to 100 cloud-to-ground lightning strikes worldwide. It's amazing when you think about that. Like every second goes by, you have that many lightning strikes across the world. You can only hear it about 12 miles away, so again, after 60 seconds, you might as well give up counting. On average, about 100 people per year are killed by lightning. The 30-year average is about 66, but what we generally see is a lot of this is happening outdoors. So people on the golf course, people on the soccer field, people standing underneath trees during thunderstorms. Don't be the tallest object and don't be outside during these lightning strikes. It doesn't have to be raining to be killed by lightning. People forget that. Lightning can strike well away, sometimes miles away from where it's raining and from the parent thunderstorm. And so you have to be aware that if thunderstorms are in your vicinity, to take shelter indoors. You can be killed even if it's not raining, even if the thunderstorm is miles away from you. And it's a very underappreciated hazard when it comes to thunderstorms. Globally, yes, we do see a lot of lightning across the United States, specifically in those thunderstorm-prone areas that we discussed earlier. But globally, we actually do see other hotbeds for lightning activity, including the tropical regions of Africa. There's a hot spot in Argentina, North Australia, places like Bangladesh and Southeast Asia do see quite a few thunderstorm and lightning strikes as well. And northern India near the Himalayas on the southern flank, we do see a lot of lightning strikes as well, with a pretty constant density over portions of Asia and Europe. This is a famous photograph taken before a lightning strike, and I don't know if I would have a smile on my face. If you feel the hair on the back of your neck or on your arms start to stand up when you're outside, take shelter immediately, because that means that lightning is probably going to strike in your near vicinity very soon. So, you can go to the Museum of Science and Industry, put your hand on the plasma ball and get your hair to stand up like that, and that's fun. But when this is happening outdoors, there's a very significant charge separation outside, and you must be aware that lightning is probably very close to striking if that happens. So I don't know if I'd have a smile on my face at that point. I'd probably be scared that lightning is about to hit. Thunderstorms can be very hazardous to, of course, aviation. So if your flight is delayed due to weather, find something else to be upset about, because these pilots and these aircraft lines are probably doing this for your general safety. Thunderstorms can even be struck, or airplanes can actually even be struck by lightning. You can see this particular plane here taking off from Japan, actually getting struck by lightning. Aircrafts get hit by lightning actually all the time. They're actually built to be able to withstand lightning strikes. The charge is conducted around the cage like a Faraday cage in these lightning strikes. So generally you don't have to worry about lightning strikes. However, the other thing that's way more dangerous to aviation is microbursts. And microbursts are very fast downward rushing pockets of air in thunderstorms that can take down aircraft pretty easily. And there's a very famous example of this in August of 1985, Delta Flight 191, where all crew, pilots, 137 people on board were killed when the plane basically stopped short of the runway. In this particular case, the flight was coming in to land at DFW. It encountered a very strong headwind from this storm, and of course, if you have a very strong headwind, that's going to increase lift on the aircraft. The pilots had to draw back the engines because they were going way too fast. They were going to miss the runway. And then they got to the other side of the storm, where they had fast, potentially hundreds of miles an hour outflow from the storm behind the aircraft. And it's like trying to run with a kite when the wind is at your back. There's no lift, and that aircraft basically fell out of the sky with no lift, and the plane fell short of the runway. After this particular event, there was a wind shear monitoring detection systems were installed at all major aircraft, and pilots generally and flight towers do not let pilots take off in the vicinity of these microburst events, but they are still very dangerous to aircraft, and are often the reason that flights are delayed, either taking off or arriving at airports when thunderstorms are in the vicinity. Some other real-world encounters that you may come into in regards to severe storms. You may experience a nice big shelf cloud like this across the horizon. Of course, very hard to see this in the Chicago metropolitan area due to all the buildings and trees in the way. But if you see a big shelf cloud like this coming around the horizon, it may be a derecho. Derecho is a special weather term that is a long-lived line of thunderstorms that's producing severe wind that can travel hundreds of miles before dissipating. The other type, a derecho may be a type of a bow echo. You can see in the radar reflectivity here, we have this very distinct backwards C shape that looks kind of like the bow of a bow and arrow. And it's really right at the notch, the leading edge of that bow, where you'll have the most damaging wind. This particular event that I'm showing here from radar reflectivity produced wind speeds over 100 miles per hour across portions of Michigan on May 31st, 1998. This was a derecho that traveled across 6 states and actually even produced some fatalities. The winds were so strong. But if you're standing here at the leading edge and looking this way, this might be a picture of what you'll see. A big shelf cloud coming across the horizon with very severe damaging wind. This may have some small hail in it, but generally when you see things like this, the greatest threat is damaging straight line winds and not necessarily tornadoes. But if you see the term derecho in the news, it's referring to a very long-lived, perhaps traveling hundreds of miles windstorm that's producing straight line winds. Here is the radar animation from that May 31st, 1998 derecho. You'll see here when I put the animation back that this particular storm started out in the Dakotas, traveled across Minnesota, Wisconsin, crossed Lake Michigan, and then Erie and Ontario before dissipating in New York the next day. The storm recorded a 128 mile per hour wind gust. This was not estimated, that was actually recorded. Its forward speed was 87 miles per hour, so you would be hard pressed to even outrun that in a car. There were 5 fatalities directly attributable to the storm, and it crossed over 5 states before dissipating. So these very long-lived windstorms can often produce a majority of the severe weather damage on any given year from wind. Hail is obviously another very damaging aspect to thunderstorms. They range in diameter from peas all the way up to 7.5 inch diameter hail. Circumference here of 18.75 inches in terms of the Aurora, Nebraska hailstone. We have very large hailstones, Vivian, South Dakota. We have, I think, a new record now that was found in May 2011 in portions of Oklahoma. These can come actually right through your roof. So if you think your roof is protecting you from hail, yes, it can damage your roof, but these larger hailstones can actually come right through the plywood into your attic, and in some cases have produced fatalities when they get large enough. Hail this size is almost guaranteed to be coming from a supercell thunderstorm with a rotating updraft, and it would take a very strong updraft to suspend that size hail in an updraft. And just to show you some of those updraft speeds that would be required, softball size hail, so a women's softball size hail at 4.5 inch diameter would need an updraft of 100 miles per hour in order to sustain it. So if you could think of taking a hairdryer and point a hairdryer up and try to suspend a ping pong ball, that would be pretty easy. But to suspend a women's softball, it's going to take a much stronger updraft in order to support that. And in this case, the updraft speeds can approach 100 miles per hour. Now, the trajectory of hail in a storm is somewhat debated. I think you look at hailstones and you kind of see rings on them, and you sometimes think that maybe this is tossed back and forth up in the updraft several times. There's some new research that basically shows there's basically one trajectory. The embryo of the hailstorm, which is what we call grapple, starts in the storm, it is lofted, it goes through either wet growth or dry growth, which is essentially a microphysical growth of the hailstone, and then once the updraft cannot support it anymore, it falls out. So really, this hail size is very dependent on this updraft speed of the storm and the microphysical growth processes that are going on within the storm before it falls out. But the bottom line here from an intro level perspective is the stronger the updraft, the greater the potential for very large hail. If you want to experience hail, the hail climatology map basically shows that you should go live in Oklahoma City, or more specifically Norman, Oklahoma. You can see the number of hail days per year there almost approaches 10. In northern Illinois, you can see that teal color. We get about 2 to 3 hail days per year across northern Illinois. This is not necessarily severe hail, just counting any size hail. But that 2 to 3 count basically is over the period 1980 to 1999. And if you look at some of the latest research, including the 2000s, the shift is not really that much different. So the Great Plains of the United States, specifically north central Texas, Oklahoma, and Kansas, do see the greatest number of hail days per year. But you can see that distribution, if you're living in Atlanta, you certainly can get hail there as well. Even New York City averages maybe 1 to 2 hail days per year. All right, let's focus in on tornadoes. Tornadoes are one of those fascinating phenomena I think a lot of people are very interested in. I want to focus just really quickly on the definition of a tornado. So you can see a tornado here is a violently rotating column of air in contact with the ground. If it's not in contact with the ground, we term it funnel cloud. Most tornadoes are very brief, only lasting a few minutes, but they can, in some documented cases, last for more than an hour, which would be pretty remarkable. Here's the average number of people killed per year. We're going to talk a little bit more about tornado fatalities in just a second. This astounding number at the bottom here, nearly half of all fatalities from tornadoes occur in mobile homes. But take a look at this chart here of the number of people that have died since 1875 in tornadoes. And what you can see is prior to about 1925, you had a pretty steady, constant chance of becoming a tornado fatality. You can see that number remained relatively steady. And then after about 1925, we start to see this downward trend in the number of tornado fatalities. And there's several reasons for that. One of the reasons is the advent of Doppler radar, which occurred in the mid-1950s and was expanded across the United States in the 70s, 80s, and 90s. Part of this is better understanding of tornadoes, advent of the National Weather Service, the Skywarn spotter training program, lots of storm chasers. So really this is a function of us getting better at understanding, detecting, predicting tornadoes, this downward trend. We'd love to get to 0 fatalities every year from tornadoes, but we're just probably not ever going to get there. And in fact, some people have argued that we'll probably either be steady for tornado fatalities as we approach the next 20 to 30 years, or perhaps we'll even start to see an increase as our vulnerability to tornadoes begins to increase as people as we're putting more assets and more buildings in the paths of these tornadoes as we go into the future. I'm not sure coming into this class how many of you would have ranked Illinois in the top 10 for tornado activity. You can see here the average number of tornadoes by state. Texas obviously takes the cake. It's a very large state. When you normalize by area, Florida actually comes to the top. Texas is still on that list. But Illinois ranks 10 on that list of top 10 in terms of average number of tornadoes per 10,000 square kilometers. So really the middle one here is the one you want to focus in for looking at the most tornado-prone areas. Florida probably is surprising to you, but Florida actually gets a lot of tornadoes associated with landfalling hurricanes. So that kind of skews the results there a little bit for Florida. But then some other traditional states that are in your colloquial tornado alley discussion: Oklahoma, Kansas, Iowa, Indiana, etc., Nebraska pop up into that list as well. Some characteristics of tornadoes: most of them rotate counterclockwise, but a few do rotate clockwise. Just depends on the supercell storm that is producing it. These are just some run-of-the-mill averaged facts. Depending on the tornado, these may not ring true. The highest wind speed ever recorded from a Doppler radar was 315 miles per hour in the Bridge Creek Moore, Oklahoma, May 3rd, 1999 tornado. But wind speeds generally range from 75 to 250 miles per hour in these tornadoes. Of course, the higher end of the scale will get you your high Fujita rankings, which we'll discuss here in just a second. And tornadoes can consist of one singular columnar vortex or several independent vortices that are rotating around like a merry-go-round around one another. This depends on something that we call the swirl ratio in tornadoes, whether or not you'll get these multiple vortex tornadoes or one singular columnar tube. Most tornadoes come from the southwest and go towards the northeast, but that is not always true. Some tornadoes actually come from the northwest and go towards the southeast, and we even have documented cases of tornadoes coming from the northeast and going back to the southwest. But by and large, on average, tornadoes do tend to come from the west, southwest, or southwest and travel east, northeast. Here's an example of, hopefully, it doesn't look like this is going to work here, but this is an animation to show you tornado formation. And really what we see in tornado formation is that we have to have some degree of horizontal wind shear. So in this particular case, let's imagine that we have wind at the surface that's fairly slow, wind aloft that's fairly fast, right? And then you can think of what would happen in the vertical profile if that were to happen. Right? So as air goes up, it's going to be tilted over. What that does is create rotation about a horizontal axis. So as you go up in the atmosphere, the air is being turned and we get this circular motion, right? So you can imagine that spinning. We take that horizontal spin and then with an updraft, we can tilt it into the vertical, which is kind of showing here in the thunderstorm profile. At the very base of that thunderstorm mesocyclone is where your tornado will be located, but the air then spirals and rises up through the mesocyclone all the way up to the anvil of the thunderstorm. But tornado dynamics and tornado formation are very complex. I think it's taught, way too simplistically when you just say, warm and cold air collide and that creates a tornado. Really, the clash of the air masses has really nothing to do with tornado formation. It's all about the wind shear profile in relation to the updraft of the storm and how much instability there is. So there are lots of different theories on tornado formation and really different ways, honestly, that tornadoes can form. They can form through this mesocyclone process. They can also form from stretching of spin. So if you have some vertical spin that's present in the atmosphere and you stretch it in both directions, like a spring, it's like an ice skater that brings her arms in closer that can spin faster and create spin fast enough to be characterized as a tornado. So there are different ways to produce these spin and these vortices in the atmosphere, but by and large, the tornadoes that do a lot of the damage are these mesocyclone tornadoes that occur in supercell storms. If you're looking at a sort of a 2D and then stacked with a 3D dimensional profile through the atmosphere of what severe storms look like, at the surface in the springtime, what you'll probably see is a well-defined cold front with CP air behind it. And on the warm side of the storm, right, our warm front, and so this would be our quote-unquote warm sector where we have maritime tropical air. The red box here is where severe weather would be likely in these mid-latitude cyclone setups. It's going to be really most anywhere in the warm sector is going to have a threat for severe weather. But as you go up aloft, we have a vertical profile here that's shown on the right, and then your cold, dry air way aloft in the storm. And so we often see that surface weather features are correlated with these upper level features. We have a strong upper level trough with cold, dry air creating the strong upper level winds. And as we go to the surface, we may have a southerly wind direction that's changing to westerly, southwesterly aloft, creating the directional shear that we need, and also the instability, right? Because we have warm, humid air here at the surface and cool, dry air aloft. So on surface weather maps where we see mid-latitude cyclones in the spring, you're very often likely to have thunderstorms and severe weather potential in that warm sector where the maritime tropical air is located. Tornadoes don't just happen in the United States or North America for that matter. We also have hotspots in Argentina, South Africa, portions of the coastal Australia region. Bangladesh is actually a hotspot for tornadoes. We see tornadoes in Japan and in China and across majority of the portions of Europe. And so you can see, obviously, frequency-wise, they happen a lot more in North America than anywhere else. But the Americas, the unique geography for the Americas is that they both have north-south oriented mountain chains. So in North America, you have the Rockies, and you can see a majority of the tornadoes happen to the east of the Rockies. In South America, we also have the north-south mountain chain, the Andes, in tornadoes happening downwind in the mid-latitudes, right? You don't see a lot of tornadoes here in the tropical regions of the globe. You see them happening outside of the tropics in the mid-latitudes, where we have adequate vertical wind shear. In the tropics, we just don't have a lot of vertical wind shear. That's why hurricanes can form there, but severe storms cannot. They don't have the vertical wind shear necessary for tornadoes. So it's really in this mid-latitude region of the world where you can create instability and wind shear that can produce these supercell storms. Focusing in a little bit more clear on the United States, I have a red outline of the colloquial term tornado alley, which I really don't like that term very much because, as you can see here on this map, tornadoes can happen in all 50 states, including Alaska and Hawaii. Yes, indeed, most of the tornadoes happen across the central Great Plains of the United States, but places like Kentucky, West Virginia, New York, Vermont, New Hampshire, Maine, they're all vulnerable and have had tornadoes in the past. But yes, a greatest frequency of tornadoes does happen in places like Texas, Kansas, Oklahoma, Iowa, and even extends into places like Indiana and Illinois and Mississippi and Alabama. If you look at the tornado The tornado alley is kind of like a C shape when you look at the climatology of tornado days per year from 1980 to 1999, with a couple interesting hotspots, including northeast Colorado and Florida, where we see a lot of tornadoes from landfalling hurricanes and landspout weak tornadoes that occur in northeast Colorado every year. So the greatest threat, no doubt, is out here in the Great Plains of the United States, but tornadoes are found again in all 50 states and can happen at any time of the year. This is not just a springtime phenomenon. We rank tornadoes, I said, on the enhanced Fujita scale, so here's a look at that scale and what it looks like. Also with the proportion of tornadoes that are occurring at each of those thresholds. So you can see about 8 in 10 tornadoes are ranked F0 or F1. About 2 out of every 10 are ranked F2 or 3, and then only the most violent tornadoes, about 1 out of every 100, are ranked violent, F4 or F5. And you can see as you go from 0 to 5, the intensity is increasing due to the wind speed and obviously the damage that is associated with those wind speeds. Now, the Fujita scale is quite different than the scale that we'll talk about with hurricanes, which is the Saffir-Simpson scale. The Fujita scale is based on damage, right? So tornadoes happen so quickly and are hard to forecast, so we can't get instrumentation out there like we can with a hurricane. Hurricanes, we can fly planes back and forth, we have plenty of time to get in the path and measure the wind speeds and the central pressures of hurricanes. With tornadoes, we can't do that. So we rely on the damage footprint that is left behind from tornadoes in order to rank them. So this creates some inconsistencies and some challenges, because if you have a really strong tornado that happens over a field and doesn't hit anything, it could get a rating EF0 or EF1. Conversely, if you have a fairly weak tornado that goes through a location that has a lot of damage or a lot of things in the way, homes, etc., it'll have a tendency to get rated a little bit higher because it has a lot of targets to hit. So it's not a flawless rating scale because it's relying on basically subjective interpretations of damage to homes. But it is really the best we have in terms of rating and ranking the damage in the scale of really trying to figure out from a scientific perspective how powerful a tornado was in a post-mortem sense. Thankfully, as I mentioned, the number of fatalities by decade has been going down. Take a look at this stat here at the bottom. Significant tornadoes were responsible for 98.8% of all fatalities. So in other words, significant tornadoes, the ones doing Fujita scale damage 2 or greater, are responsible for most of the fatalities. In this case, 2/3 of all tornado deaths were by violent tornadoes, yet they only accounted for 2.1% of all tornadoes. In other words, it's the violent tornadoes, the strong tornadoes, the ones that are producing the fatalities. And I don't think that's too hard to understand, but this distribution of fatalities is actually what's a little bit more interesting to understand where people are dying from tornadoes. And it's not really the locations that you'd think due to some unique socioeconomic vulnerabilities. So I'll show that here in this particular map. So what we essentially have here is in the bottom left, you kind of have your idea of tornado alley. So this is a smooth frequency of tornadoes. The top, we have basically killer tornadoes, so you can see what that distribution looks like, and then significant tornadoes here in the bottom. So I want you to really focus on map A up here and map B. Okay, so again, B is like your tornado alley, like where tornadoes occur, and A is tornado fatality alley. In other words, where are people dying from tornadoes? And you can kind of see, right, a peak here, Texas, Oklahoma, Kansas, Nebraska for tornadoes. But tornado fatality alley is more like northern Alabama, Mississippi, western Tennessee, Arkansas. So there's this shift, right, from where tornadoes are occurring to where people are being killed by tornadoes. And so I could just pose the question is, why does that area have a disproportionate share of the casualties and fatalities associated with tornadoes? And I'd like you to just think about that for a second. Why do we see more tornadoes in the Great Plains, but more fatalities in portions of the Mid-South? And it turns out there's a multifaceted answer with lots of different complex socioeconomic vulnerabilities that are coming in here. So first is really a physical difference where we see a lot more nighttime tornadoes in this area. So you can see in Tennessee, Kentucky, and upwards of nearly half or over half of the tornadoes in these states are after dark but before sunset. So basically it's dark out. And these are happening at night, and of course tornadoes at night, very, very difficult to see, very, very challenging to warn for from as you're a forecaster, much more likely to produce fatalities. In that area of the country, we also see a lot more forest cover. So the physical landscape is just different, right? We see a lot more trees. If you go storm chasing, you're probably not going to go to Arkansas. You're not going to go to Mississippi. You're going to probably go out here to the Great Plains where you can see from hundreds of miles in all directions. And so if it's at night with trees in the way, it makes it even more difficult now to spot these tornadoes as they're approaching your location. I said at the beginning of the lecture, a lot of the tornado fatalities that we see are in mobile homes. Well, look what happens to a mobile home, right? When it gets hit by even a weak tornado. This is F1 damage, but these mobile home structures are completely demolished or rolled by these tornadic wind speeds. And then if you look at another vulnerability here, right? Same locations that experience night tornadoes and lots of trees now have a very high percentage of weak frame housing stock, somewhere between 30 and 60% in some of these counties in the Mid-South, leading to a very unique vulnerability for tornado fatalities, right? It's kind of like the perfect storm here. We have lots of weak frame housing stock, so very weak structures. We have tornadoes happening at night, and we have tornadoes happening in the trees. And so if you plot out the number of people that have died in mobile home deaths, kind of get that bullseye showing up in the Mid-South of the United States, where we see a lot of these mobile home fatalities showing up in the Mid-South, which is a really unique area in terms of mobile home fatalities. Here are some other reasons that I've listed here, 1 through 9. They still get tornadoes. It's not like the Mid-South doesn't get tornadoes. They're more likely to occur at night. Storm speeds are a bit faster because of when the storms are happening in the year. They tend to happen earlier in February, March, and April when the wind shear is a little bit stronger. More mobile homes, percentage of forested land, higher population density, so just more targets to hit. Lack of a focused tornado season. This is one I want to expound on just a bit here in just a second. And there's lots of other human vulnerabilities as well. Coping styles, religion, education, warning system distributions. All of these tend to just increase the vulnerability and the fatality rates in this particular region of the United States. Let's talk about number 8 here just a second. The complacency and lack of a focused tornado season. So I've constructed here really just 2 frequency diagrams throughout the annual cycle. So starting in January and going through December. This is just number of tornadoes just on a broad scale for Amarillo, Texas, and also for Atlanta, Georgia. So if you look at the tornado climatology for Amarillo, Texas, one thing that you see, there's a big spike in late May, early June, and then a secondary peak in November before kind of going flat for the rest of the year. In other words, if you're experiencing tornado watches or tornado warnings, right, in Amarillo, Texas, it probably goes something like this. Nothing, 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 tornado watch, tornado watch, tornado watch, nothing, nothing, tornado watch, end of the year. But the tornado frequency in Atlanta is a lot different. It might be something like nothing, tornado watch, nothing, tornado watch, nothing, tornado watch, nothing, tornado watch. And so you have a broad risk that exists all year long versus this very focused risk that happens in May and June in places like Amarillo, Texas, right? This breeds complacency in places like Atlanta, Georgia, where you don't have the magnitude of the risk that you see in Amarillo, Texas, but you have this low-grade risk that exists all year. And these low-grade risks, when you're talking about hazards, really do breed complacency versus the high-magnitude, very focused risks that we see in portions of the Great Plains. So this all has to do with tornado physical climatology and just changes in the actual ingredients that are present to create supercell storms that then produce tornadoes. So this tends to breed complacency across the Mid-South. And before we finish up this unit, I want to debunk some tornado myths that I often get in my intro classes from students asking questions. Tornadoes avoid downtown areas. I'll show you in a second that is absolutely not true. Stay in the southwest corner of your basement. That really has no bearing. Tornadoes can come from any direction. Bridges or overpasses do not offer safe shelters from tornadoes. Don't spend time opening up your windows to minimize destruction. The tornado has plenty of debris and will break the windows for you. Mobile homes do not have giant magnets in them that attract tornadoes. the visual appearance of the tornado has no bearing on the strength of the tornado. So just some of these here that, myths that I've heard over the years, sort of urban legends that need to be debunked as we go forward in our society, because many of them have absolutely no bearing on the truth. Here's some pictures of tornadoes hitting downtown areas, including Salt Lake City, Atlanta, that was hit in 2008, Dallas, Fort Worth, Omaha. We have several images of tornadoes impacting downtown business districts, and definitely very vulnerable. When you think about even Chicago, right? Chicago, the downtown business area of Chicago was hit in the late 1800s, and it's going to be a matter of time until we have another large tornado event in the Chicago metropolitan area that will no doubt cause billions of dollars of losses. We just have gotten very, very lucky in terms of missing tornado events really in the past 20, 25 years across the Chicago metropolitan area. So that's it for Unit 15. I want to just say a couple of things about tornado watches and warnings. So hopefully you know that a tornado watch is issued when the conditions are favorable for tornadoes, not necessarily that they're going to occur. And also that a tornado warning is twofold, right? Tornado warning means tornado has either been spotted by a trained weather spotter, or rotation has been detected in a storm that leads a forecaster to believe that their tornado might be present. And our tornado forecasts, by the way, are getting much better than they used to. You can go to the Storm Prediction Center website here, spc.noaa.gov. They provide severe weather outlooks as many as 8 days in advance. And just like the Homeland Security threat level, will give you varying levels of severe weather and tornado threat for any particular day. And so you can anticipate maybe when the conditions will become favorable in your area for severe storms. These are not watches, these are not warnings, but these are just basically highlighting areas on a daily basis that may be prone for severe weather. And this was actually in November of 2013 during the Washington, Illinois tornado. The Bears game was going on at Soldier Field, and we had a high risk of severe storms and tornadoes across Illinois and Indiana. And I'll just show you that the forecast for that particular day was very good. The red dots here are tornadoes, the blue dots are damaging wind reports, and the green dots are large hail reports. And you can see the forecast for that particular day for tornadoes was great. There was a long track F4 tornado that started near Washington, Illinois, and tracked through the town of Washington, causing F4 damage on the north side of town there. That storm went on to produce another tornado near Coal City on November 17th, 2013 as well. So our forecasts are getting pretty good for tornadoes because we understand the environment that they occur in. We're not perfect at forecasting these, but we're certainly getting better with our better computer models and better understanding of how tornadoes work. So hopefully you've learned a little bit about severe storms and tornadoes in Unit 15. Again, there's several other classes offered here at Northern Illinois that investigate things like radar signatures in tornadoes or just severe and hazardous weather in general. So if you're interested, check out those courses. Otherwise, we'll see you in the next unit.